Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on June 26, 2025, just over a week ago. This paper shows that simply moving from offline to online fine-tuning can boost a model's win rate by over 56% on key benchmarks. The paper is titled, Bridging Offline and Online Reinforcement Learning for LLMs, 2506.21495 versus 1, and its findings suggest a more efficient path for training powerful models. It systematically compares different fine-tuning methods, revealing that even occasional model updates can dramatically boost LLM performance. Alright, so to really unpack what they mean by these different training methods, the first figure lays it all out visually. It shows a generator model creating responses or rollouts from prompts. A reward model then scores these rollouts, and those scores are used to update a separate trainer model. The crucial difference is how often the generator is updated with the trainer's latest knowledge. In offline training, it's never updated after starting. But in semi-online or fully online training, it syncs periodically or even at every single step, allowing it to learn continuously. So looking at the hard numbers, this first table details the results on verifiable math tasks. It compares several training methods, including one called direct preference optimization, or DPO, which is a technique for fine-tuning a model by showing it which of two answers is better. We can see that offline DPO improves on the base model, but the online and semi-online methods are in a different league. Across all three math benchmarks, they consistently score much higher. What's really surprising is that semi-online direct preference optimization, updating just every 100 steps, performs almost as well as the fully online approach. Okay, so that was for math problems with clear right or wrong answers. This next table shows what happens with more open-ended, non-verifiable tasks, like following complex instructions. We see the same pattern here on the Alpaca Eval and Arena Hard benchmarks. The online and semi-online direct preference optimization methods just blow the offline version away. For instance, the win rate on Alpaca Eval jumps from 53% to over 83%. The results also include another method called Group Relative Policy Optimization, which performs well, but online DPO still seems to have the edge. Building on that, this final table explores what happens when you mix these different task types. It tests for something called cross-task transfer, which is whether getting good at one skill, like math, helps with another, like following instructions. The results show not really. A model trained only on math does poorly on instructions, and vice versa. But, and this is the key insight, a model trained on both the math and instruction following datasets at the same time performs well across all benchmarks. This suggests that combining different reward types is a powerful strategy. So those are the high-level results, but getting these online methods to work well involves some key details. These plots show one of them. They compare the standard online direct preference optimization with a version that doesn't update its reference model, which is a stable baseline used during training. On the left, you can see that without this update, the model's response length just collapses over time, and the plot on the right shows this directly hurts performance, as the reward score drops significantly. It's a clear demonstration of why this synchronization is so critical. Now, another interesting behavior the authors observed is shown in these plots. They look at a metric called logit entropy, which is basically a measure of the model's uncertainty. When entropy is high, the model's considering lots of different words for its next step. When it's low, the model is much more confident. The plot on the left shows that for all the online and semi-online methods, this entropy drops sharply. The model gets more certain as it trains. And this isn't because the answers are getting shorter. The plot on the right shows response lengths stay pretty stable. So to wrap things up, this paper makes a really strong case for moving away from purely offline fine-tuning. The key takeaway is that online and especially semi-online methods, where the model is updated periodically with new data, dramatically boost performance across all kinds of tasks. That semi-online approach is particularly compelling, offering a sweet spot that balances top-tier results with computational efficiency. It's a clear path toward building more capable and robust LLMs. That's all for this edition of the AI Research Roundup. Thanks for tuning in.